Okay. So I'm going to just go through this lecture handout, picking up on the example, and we're going to finish up synchronous machine and then go to DC machine. Now this generator example we started in the last lecture. I gave you what you typically will get with a synchronous machine is a data sheet. Most synchronous machines, in my experience, are custom designs. They're larger machines. There's some that are just commercially available, but it's really the DC machines and the induction motors that are really the ones that are used the most. But synchronous machines are used by the utility industry and in renewable energy and specialty applications. But the synchronous machine is really the foundation of how everything works. That's why we spend so much time on it. But so you'll see all of these things that we're learning here are going to flow over into the other machines. So we were looking at a 2-pole machine. It was a 250 kVA, so this would have been kind of a, it's a machine that might be used for a small wind generation or something like that, or a building-sized generator. That's the idea here. It's a 690 volt. It's a lower voltage machine. And we found these variables in the last lecture. The mutual inductance, the short circuit current ratio, the per unit reactance, synchronous reactance, the base quantities, and then the synchronous reactance. I also pointed out, synchronous speed and RPM and how that actually relates directly to the electrical frequency. And it's the same as the rotor speed because it's a synchronous machine. And then we looked at taking this machine that we had all the data from and said, why don't we operate this as a generator? As a motor. And the setup is shown right here. And then I said, we're going to operate this thing, and we didn't actually start to work this problem out. I just gave you some of the background information that you would need. But what we said, what I'm asking you to do is find, 4 things here. The first is, let's find the EMF voltage under a specific load condition. And I gave you this load, introducing a new idea here of writing power in terms of horsepower, not megawatts or kilowatts. Also talking about the idea of shaft power versus the mechanical power applied to the shaft. So shaft power is really the shaft power that's applied to the load. And so this gets into, the application of the motor and the thing that it's driving. Also, since it's a synchronous machine, you can control the input power factor of the machine. And so this machine is being controlled to operate at a 0.9 leading power factor. And then we introduced the idea of the mechanical efficiency as well. So first thing is find EAF. So let's just go through the number 1. Okay, so we have a shaft power of 268 horsepower. Now if we would neglect the armature losses, and we assume that the field is applied from a separate supply or generator, then the power that is delivered to the shaft, and that's different than the shaft power, and I'll just show this graphically in a moment, that is going to be equal to the input power at the terminals. So the basic idea is this: if you look at a, here's the motor, and I'm kind of drawing this schematically here. It's a synchronous motor, and you're connecting it from the three-phase feed supply. So you got your A, B, C windings here. And you can, imagine that you've got your upstream transformer feed supply here. We've got the 690 volts line to line. If you were to put a power meter on this, just like we have in the lab, you would see you'd be able to measure an input apparent power. That's what we call S-in. That's the power into the motor. Now the motor ultimately is going to be feeding some load, so mechanical load. It could be a big pump or something, a lot of different things it could be. And it's rotating at a speed, mechanical speed, omega r. And we think about torque, so the applied torque it's along the shaft in this direction. So there's an applied torque to the shaft that's typically called T mechanical. There are losses on the shaft. You can write them even in terms of a torque loss, but there's not all of the torque gets to the load because of these losses. A lot of times, for example, they have a big fan on the shaft to cool the motor. That's a loss. There's friction and other things like that, the bearings, things like that do this. Question or no?
Yeah, would slippage technically be considered a mechanical loss? Would that be considered more of an electrical?
You're talking about mechanical slippage?
Well, I know in motors there's always, at least when I'm at work, they always tell you how much slippage there is with the motor.
Yeah, I'll tell you what, that's different. That's a totally different thing we're going to introduce with induction motors. It has nothing to do with this. And actually, it shouldn't be called slippage. It's slip. If I called it slippage, I might think it's a mechanical, that somebody didn't do a good job of coupling it to the load. That would be a loss. Anything that anybody messed up.
Yeah, the people who make our induction motors, they called it slippage, and I was like, what the hell is slippage? Okay, that makes more sense.
Yeah, there's these colloquial terms that spring up. I know I grew up with them in my house because my dad was a mechanic. Yeah, and it's nothing wrong, but a lot of these words just take on a life of their own. But anyway, yeah, so these losses. Now, we also told you that the power, so there's a mechanical power that would be equal to the product of the speed times the torque, the T mechanical. There's a shaft power. That's the speed times the shaft times the torque of the shaft. So there's a relationship between power and torque that you can use to find torque or power. Now what you have in your motor is there are electrical losses in a synchronous motor. So here's the electrical diagram of one phase. You remember we had the RS and we have the JXS here. And then we've got the EAF right here. So this is one line to neutral representation. Okay, so there's I squared R losses here, but they're very small, so if we're neglecting them. And there's another loss. A lot of times with synchronous machines, the field, they actually run two generators, and we don't go into this in this class because it really gets into some complexity. But it's almost like they have so it could be a motor or a generator. And they call this is your main. That's what we're talking about here, that has the armature in it. And it's got a field winding on the rotor. The field winding gets fed, some ways they do this, they have a generator on the shaft. This is called an exciter that provides the field. So we are neglecting this right now. It's not here. We're assuming that the field power is coming in externally from some other place. So there's no field winding losses and there's no exciter losses. So in a real machine, you would also have these other losses. So if that's the case, the input power, the real part, essentially the real part of Sn, looking right from the input, is going to be equal to P mechanical. That's because we're neglecting all these electrical losses. So we can just work our way back from the shaft to the input power. And so that's what we do right here. We say, let's take the P shaft. We know that is giving us its 268 horsepower. There's a mechanical efficiency because of the losses. So that means that it's going to be, we have to have more power. Taking the P shaft divided by the efficiency, that's P mechanical. That's applied to the shaft. We have to convert it to watts again, 746 watts per horsepower. So remember this conversion, and usually on a test I will give it to you, but I don't know if this is a take-home exam. I mean, it's not take. Well, I'll give it to you. I don't like it. I have to get that. But it's a good thing to have in your notes to save time. And then you just plug in what we know, and we get an input power of 204 kilowatts. The input apparent power, then, what is that? That might be important here. In fact, it will be important. So the input apparent power is, remember that that P, right? P is equal to S times power factor. And so S would be P divided by power factor. And that's what we do right here. So we have a magnitude for the volt amperes applied. We've been given the power factor angle. We know that it is a leading power factor. And remember that a leading power factor gives you negative VARs. So there's a negative on the power angle. And then as a result, we plug all this in, we're going to get 227 kVA minus 25.8 degrees is our power angle. And now go back to this machine. This was a 250 kVA machine. So we're not running at the full power rating. We're running lower. We're running at 227 kVA. And so we need to know the input apparent power to find the line current. So the line current is going to be apparent power divided by square root of 3 V line to line RMS. We plug in everything we know there. It's a 690 volt line to line. And we get 190 amps RMS. Again, going up to the specs for the machine, we found a base current, which actually is the rated current. It's 209. So we're less than that. We're running at 190. the input power factor is the negative of the power angle. So we know the full phasor representation of current now. It's 190 at 25.8 degrees. And now we can use the equivalent circuit for the motor, and we can solve. We're trying to find this. We're going to find that using phasor math. So this is the phasor equation. We're going to do it completely mathematically here. So we need to find VA. VA is the line to neutral voltage. It's not the line to line voltage. This is number one big mistake everybody makes on exams, okay? If you're going to do anything to prepare for the exam, when you go to sleep at night, say divide line to line voltage by square root of 3, just 10 times before you go to sleep at night. That'll put you right to sleep. But anyway, there's your line to neutral voltage right here. It's referenced to 0 because you've got your power factor measured from that point. Here's the current, and here's the synchronous reactance that we found in last period. So now you've just got to do your math. I'm going to make this into an addition right now by moving the negative j becomes negative 90, right? So let's highlight that. Here's a negative j. That's a negative 90. I'm going to add that to the power factor angle here. I'm going to get the total angle right there. I'm going to multiply together. Actually, I made a mistake when I was writing this. I got the right answer, I think. What did I do here? Shoot. So that is 190. I see, I left the 1 off. And I did this late last night. That was not good. Okay, so we got 190 here. I got to recalculate this now. 190 times 1.16 is 220.4. So this was wrong. There's the, okay, now what we've got to do is convert this to phasor. And so I'm going to take, so this is wrong. So we're going to take 220.4 times the cosine of 64.2, and that's 96. So I'm going to basically say, I'll just write out the extra steps here. 398.4, that was the line to neutral voltage, plus the real part of along the real axis of the E, that's 95.9. And then we've got a negative angle there for the imaginary part. We're going to take 220.4 times the sine of 64.2, and that's 198.4. Okay, so you got that. Then we can just add everything up together. That's 398.4 plus 95.9, 494.3. And then we're going to have a negative j, 198.4. And then let's convert it back into polar form by taking the sum of the squares, square root. 532.6. I'll just round it up to 533. And then the angle will be the inverse tangent of the ratio of the imaginary to the real. This is the kind of thing you need to make sure you can practice, because you will inevitably have one or two problems like this on the exam. So that's minus 21.9 degrees. Okay, there we go. So here's the answer. Whoop. There's the answer. Okay. Questions on that? Clear to everybody?
Pretty clear.
All right. So we found it. This is how you do it. Now, number 2 was what? Second thing is, for this condition, we're going to find the field current. So we did a no-load test on this, and there was a field current, but obviously the field current has to change when we put this thing under load to get the outcome that we want. So what we're going to do is apply this equation. This is from one of the important equations that you've got to have in your notes, relating the field current to the EMF voltage amplitude in RMS. That's why we have the square root of 2 times that, and relates it to the electrical frequency. And so this is the field current now. It's 9.1. And remember that in the lecture last time, we did the open circuit test gave us 8 amps, what we call the AFNL, right? Ampere field no load amperes. So we actually had to increase the no load amperes that we used to get rated voltage at the terminals in order to operate this as a motor and get the leading 0.9 power factor. So the third question is find the mechanical shaft torque. Okay, so we have already in the last lecture, this is a repeat of what I just told you, that there's a relationship between torque and power. And I'm saying that the P mechanical is the power applied to the motor shaft. That's really my definition. The book is not super clear on this, but this is in engineering practice. The shaft power. If you always assume that you're given a horsepower and it's shaft power, and that there's some mechanical efficiency, that gives you a little bit of margin in your design. And so it's always a good idea to make this assumption, even if it's not given, because, practice isn't consistent in the way people describe this, isn't always consistent. Now this torque that we get is really correlates very much to the torque that we found in Chapter 3. It'd just be an extremely complicated expression, and I gave you the notes my student developed, which could get you about 80% there. A couple years ago, I had a really great student who became one of my grad students who put that little note together that I shared with you 2 or 3 lectures ago. But this is how it does. It's really the same thing, okay? Because we're neglecting losses. Now, what about the shaft torque? Here's another way to get shaft torque. So I already said it's this, right? Take the Tmech, multiply it times that efficiency. You could also say, here's a shaft power, which is the difference between P mechanical and P rotational loss. And we're going to do a couple practice problems with this with DC machines, looking at it this way in the next module. This rotation loss is like, well, this is what Brandon was talking about. Friction, windage loss is another word for it. Some people use stray load loss, which is really a catch-all for everything. And generally, the technically correct definition of stray load loss includes electromagnetic losses such as proximity losses and things that aren't so simple to calculate in machines. Okay, so if we know this, I'm going to say, well, what do I have? I know P shaft. We found 204 kW. What's the mechanical speed? Now, I wrote this down. We talked about it last time, and we'll see this quite a bit. The relationship between the rotor speed and the electrical frequency is 2 over poles times omega E. You might see this more often than we even see this when we first introduced what is omega E. It's poles over 2 times omega R. It's just going the other direction here. So because it's a two-pole machine, these things cancel out. And it's quite just this. And there's your torque. It's 541 Newton meters. You got to make sure that you use watts when you do your shaft calculation. Okay, questions on that?
Not really.
Okay, good. Now let's go. Now what's the last one I asked was 4. Number 4 is use the phasor I reworded this, and I'm going to be clearer on this now too. In the last exam I said, actually I didn't do this on the exam except for a very special case. The phasor diagram, if I ask you to do it, why do you do a phasor diagram? So we're going to use it to verify what we found in 1 graphically. And so to answer number 4, this is a 4, not a 3. So we'll go back to number 4 down here. We need to find the per unit values for everything. So we provided a base. The base is, this is the line to neutral nominal or rated voltage, 398.4. We're operating at that voltage. So this is a 1. And it's at 0 degrees, so it's really just 1. The base current was 209. We're operating at 190. We've got a 25.8 degree angle, so it's 0.91, 25.8 degrees. The EAF we found, now I have to recalculate this. It was up here, 533. So let's write that down here. Quite a bit higher than the nominal voltage. And then the angle was minus 21.9. Hopefully I didn't make a mistake there. It looks like it's right, but feel free to figure these out yourself to check them. Minus 21.9, and then the ratio of these two voltages, 533 divided by 398.4. 1.34. Okay, so there we go. Now, okay, here's a phasor diagram, and we went through this last time, and I recommend that you practice this. Find first the voltage phasor. It's on the real axis. There's your imaginary axis right there. Then put on the phasor current, which is 0.91. So this is the fact that we're in per unit is nice, because for some machines, if this was like a 10 megawatt machine, you might have 2400 volts line to neutral and 50 amps. And so what that would be, like, you would have this little goofy thing, like you'd have this is 2400 volts here, and that's 50 amps, right? That's why then you're going to try to find you might have, a little thing here. You're going to say, okay, let's find the E right here, and you have to have a microscope to see what you're doing. This is why you go to per unit. So this is 91% of the rated, right? You can think of per unit as a percent. I'm running at 91% current. This is the angle, 25.8. I have to use my per unit reactance. You can also say I'm running at, it's a 62.5 per unit reactance, or 0.625. So you take 0.625 times 0.91, you get 0.57, but then we have to do this addition right here. We're doing this math, this thing here. So we have a vector addition, the minus j. So we have to shift by negative 90 degrees the current and scale it. And we get it right here. And then we should be getting now I'm guessing this is this angle 25.8, I'm doing my eyeball here, so I'm not exactly 100% right on, but it's probably pretty close. So I draw this line here. If I was right on all my angles, about 133%, 1.33 times the nominal. That's what it should come out to. Does that make sense to everybody?
I have a question real quick.
Yeah, sure.
So in diagram, you're adding excess IA to IA. It should be added to VA, right?
Oh, you're right. Thank you. Okay, let's rewind. You're right. Okay, thank you. I got a little bit hurried here. Yep, that makes maybe more sense. There it is there. Right? Does that make sense? Now, I think this angle, I think this angle might be a little bit off. So let's try to, I'm eyeballing it. And if you do this on exam, I don't expect people to be Leonardo da Vinci, okay? It's just the rough basic idea here. I'll just redraw. Okay, I got VIA. If I had 45 degrees, I'd be right about here, right? That's about 0.9. So we go around, we're right about there. Okay, so we're going to scale this by 60% and shift it negative 90 and add it to VA. And we are getting, so this was 25 and it's 22. So, the difference in these angles isn't very much, but it's negative. And I think the important point I'm trying to say is that this angle should be negative because it's a motor. This is your torque angle, actually, your electrical version of
When
the
it's a
torque angle.
generator, we shift 90 degrees the other way, right?
It will be positive if it's a generator. There's no 90 degrees here.
I mean, when we're shifting the current after we multiply it, and to get our.
Oh yeah. No, you're right. Yes, it would be a positive. Yeah, that's what I want you to practice. That's what I say here. Okay, that's perfectly correct. I have to tell you one more thing here. What if we go back and we look at this machine and we say, okay, it's now a generator. And if it's a generator, again, we're just going to redo our no-load test. And what if we reconfigured the windings, if you could do that, or you have a different machine, it's the same machine, but they rewired it to be a delta, and there was a homework problem like this. What does it do to LAF? And I'm going to just say, well, what does it do to XS, to the synchronous reactance, just to tie everything back here. So what you're doing again is you're running this open circuit test. You're running at the no load current, 8 amps, same current condition. I'm going to do it again with the machine, but it's rewired. Now the key point is this. This is a phase. That's representing the physical phase of the generator. We're just moving that physical phase and reconnecting it. So it's kind of like you're just saying, okay, I'm going to take this guy here, sorry, I got messed up here. Okay, the physical phase, it's kind of like I got one of these guys. This is, say, phase A, and I'm going to take this phase here, and I'm connecting it up here like that, and so on, right? That's really what you're doing. And so essentially this physical phase is being moved into a different position. What you use to analyze the machines and to find EAF is the line to neutral, not the phase voltage. So the line to neutral voltage is really, it's kind of a virtual voltage now. There's a virtual neutral in the middle of everything. And so obviously you can see that the voltage is going to go down. And as a result, the inductance is going to go down. The effective line to neutral inductance because of the winding reconfiguration. So you've divided your line-to-line voltage is now, see, this was the line to neutral voltage here. That's V line to neutral is across the phase. Now that becomes the line-to-line voltage. So the 690 line-to-line, you now get 398. So you change the machine from a 398, from a 690 machine to essentially a 400 volt rated machine. So essentially you took a low end of the medium voltage machine in the US and you moved it to the high end of the low voltage machine in Europe. You know, that's one idea here, right? And so your line to neutral voltage is going to change the same way. It's now 230 volts. Now we're going to use this expression here and come up with a reduced line to inductance. Is that clear to everybody? I know some of you probably already had to do this. It was in one of the exam homework problems.
Yes.
Okay, great. Okay, now the next thing is the synchronous reactants, and it's a little bit tricky. What I want you to recall here is, and this is going back and applying what you learned at the very beginning of the class between delta windings and Y windings, we have a phase impedance. It is a phase impedance. It's 1.16. That's what we found there. If we connect the phase impedance into a delta circuit, then the phase impedance becomes the delta impedance. And this can be a little confusing because if you look at this machine, the phase impedance, which try to circle here, it was this thing. That's the phase impedance in a line to neutral, but now the phase impedance becomes a line impedance, line to line impedance, or a delta impedance. And so remember, we had this expression from the very beginning of the class. There's a factor of 3 difference between the Y and the delta. And the synchronous reactance then for this rewound machine has been divided by a factor of 3, and it's this. Now here's a check on this. You could look at it a different way. If I rewind the machine, I've changed the ratings of the machine, and therefore I could say, well, I've changed the base values for impedance. So the V base now is lower by a factor of square root of 3, and the I base is higher by a factor of square root of 3. And really, if you remember, Z is really what? Z is equal to, if you've got a V divided by square root of 3, your original, and your I multiplied by square root of 3, then what you end up with here is a factor of 3. This is your Z, this is Z prime, and this is your Z original. So essentially, use the same idea. I've got a new base impedance that is 3 times smaller. Multiply that times my per unit reactance, and now I have the same reactance. Okay, does that make sense to everybody?
Yeah.
All right, so this is it for this module. We're going to go into the DC motor. So anybody have any questions? And otherwise we're going to move on here.
I just had one real quick question when we were doing the phasor diagram.
Yeah.
Is it typical for EAF to be larger than the nominal voltage, or is that just an abnormality with the problem?
Well, it's not an abnormality. Go back to what we talked about last time. I did this at the very beginning last time, and I showed you if I was a motor, and that's why I say go practice this. If I run with a lagging power factor, EAF actually becomes smaller than the line. So it has to do with the power factor angle. And it really, yeah. Does that make sense?
Yeah. Okay.
And the EAF is proportional to the field current. And therefore, and I made the point about the leading power factor then is going to have higher losses in the field, more heat. And then it's the opposite with the generator. You run a lagging power factor, your EA is going to be higher. If you have a leading power factor, your EA right here is going to be lower. And I'm now looking and referring to the Module 6 notes that are up on Canvas. And there's a lot in here that we're going to skip, but it's good insights And we're really going to not pick up until we get right to this, let's see, right here. So this is slide 17 of the notes. And I'm going to make a segue from the synchronous machine over to the DC machine. A synchronous machine is essentially, so here's your synchronous machine right here. Put a little check mark by it, right? And there's your DC machine right here. A DC machine is an inside-out synchronous machine. That's one point to make. What does that mean? Okay. Now that fundamentally every electric machine has two fundamental windings as far as what the windings are functionally doing. When we get to the induction motor, we'll find out that these functions are virtual. They're not physical, but they do exist. In the synchronous machine and the DC machine, these functions can be exactly correlated to physical windings of the motor. So essentially I'm showing the green here is what's on the rotor for the synchronous machine. So what I'm talking about here is I'm talking about this. There's an MMF associated with the rotor field windings, and that MMF is associated with the field. So I'm saying the field's green, right? So we have the field windings, and that MMF is moving. It's rotating at the synchronous speed. There is a MMF associated with the stator windings, FS. That's the armature MMF. That's why it's a blue color. And we've got these blue windings, and I'm just representing now the combined three-phase winding MMF all together as one winding, and you'll have the MMF pointing out here, and it's rotating, and it's off from the field winding by an angle. Now this is a little different than the way we explained it originally. I have an FSR, that's the del between the rotor and the stator windings. That's what we were calling del mechanical. Now there's a combined MMF in the air gap, that's FSR, and stator rotor. And when you're at no load, for example, well, let me try to explain this. Yeah, when you're at no load, FSR is going to line up with FR. So at no load, there's no torque. The del R term, which is right here, is 0. And it will turn out that the del S will also be equal to the del R. So essentially you're going to have no angle. But the bottom line is that the combined impact of these two little angles here, and this was really kind of correlating, if we had more time, to really drawing this back to what we studied in chapter 3. And you have to do some significant amount of trigonometry to come up with everything. But this del SR is the mechanical version. I'm going to put a little sub m. It's the del m. And then the del that we find, so in the asynchronous machine, we have an EAF, that's an electrical version of everything, has a del or a del E, and the del E is equal to poles over 2 times the del mechanical. That's the difference. Okay, so the point is the synchronous machine, though, all of these MMFs are moving together at the same speed in synchronism. When you go to a DC machine, what do you do? With the DC machine, you move your field to the stator. So that's why it's inside out. And we move the armature to the rotor. And we talked about this at the beginning of Module 5 when we first introduced. We also talked about this at the end of Module 4 when we introduced the basic rotating machine and torque production from Lorentz force law. Now we have a field MMF here that's blue associated with the rotor, which is the armature. And we have a MMF associated with the field, which is now it's on the stator. And so what has happened here, we have another little thing called commutator and brushes to get the current onto the rotor. And these commutators act in a manner to switch the polarity of the current as this thing is turning. And as a result, what it does is it fixes these MMFs and the associated fields in space. They don't move. So essentially, here's the key thing, and this will be on the exam of the final exam. Rotating MMF in a synchronous machine, it's stationary and not moving in a DC machine. So the synchronous speed, the speed of the flux, is 0 in a DC machine. And the DC machine is physically constructed to get a 90-degree torque angle. In the round rotor, wound field synchronous machine, you can't get 90 degrees. It's physically impossible because of the synchronous reactance. Okay, any questions about that? Somebody tell me you're still there because I can't, I'm operating blind right now.
All good.
All right. Let me just do one quick thing. All right, now we're going to lose too much time. I'm just going to keep going here. Okay, so we talked about the commutator brushes, and I encourage you to go back, look at the recorded lectures if you don't understand this. Again, this concept will be on the final exam. The DC machine has a mechanism that both gets the current into the rotor. Okay, so the commutators and brushes really do a number of things. They get the armature current onto the rotor. The second thing they do is they perform essentially a mechanical diode rectification. So they actually convert AC to DC. The third thing they do is because of how they're placed, they ensure del is plus minus 90 degrees. If it's a generator, it'll be plus. If it's a motor, it'll be minus. Now, to kind of help you remember why this is actually the thing that you can kind of imagine when Edison hired Tesla. This is the first thing Edison told Tesla. Tesla told Edison. The first thing Tesla told Edison. Edison was like a tinkerer. He played with things until they worked, and he slept about 2 hours a night. And, he was a great inventor and businessman, but he didn't understand the physics of what was going on. And a lot of people didn't understand this. Tesla really understood this. The DC machine was around a long time before the synchronous machine. And the DC machine was really kind of a physics experiment that turned into a useful thing. And Tesla said, hey, all machines are AC. There's no such thing as a DC machine. There actually is a DC machine that's purely DC. It's called a homopolar machine. And if you want to understand what that is, go Google it and find it on YouTube. And I talk a little bit about it in my drives class. But all machines are AC. It's just that you have to have some mechanism that, if you want to make it effectively DC, there's something that does a rectification or a realignment of the fields with respect to each other in some way. And that's really what the commutator and brush does. And so, any questions on that? I hate doing PowerPoints, but we're kind of going to do this just to be efficient. Okay, so I'm going to try to drill down into this commutator. We had done a very simple explanation of what is a commutator. It's a little copper ring that is sitting wrapped around, or it's part of the shaft. And then you've got these brushes, that are riding on it. And if we were together, I would be sending you around one of these, and you could take it apart and look at it. And so what happens is, as the rotor shaft moves, it flips rotational direction at these gaps. But I'm only showing one segment, and that really, each segment aligns with one coil, which is in one slot. And from what we learned, that's a poor utilization. You really would want to distribute out the energy. And so what we have here is, physically what you really do is you have multiple little segments, see? Each segment has a little wire that connects to a coil end. And then it just flips multiple times as you move around this machine. The field is just like an electromagnet. And in fact, in a permanent magnet machine, they just replace the electromagnet with a real magnet. So you say, here's the north. So you say north, south, if it was a permanent magnet. I'm sorry, it's the other way around on the bottom here. So it's the other way around. North, right? And here's the south. And then here's the south, and there's the north. So you've got this magnetic field, that's going in this direction here. And it's not moving, it's fixed. And these commutators are fixing the rotating armature MMF in space at a 90-degree displacement. So you can kind of do a right-hand rule. You can say, okay, what's happening here is I've got the current in my electromagnet of the field. If I'm doing this with current, I'm putting in the field current IF. It's going in where the X is. It's wrapping around. It's coming back out here. Somehow it's coming back around over here, going back in, and then it's coming out here. So this is like at the very beginning, we learned wrapping this thing. Everything that is gray here is iron, and the flux lines are flowing around the back iron of the stator. And often they don't call the DC machine a stator. This is a stator, they call it a yoke, because it's holding the field in place. And then what's happening with the, because of the commutators, you can see the X's here. and there's a little X right here, X, X. So everything on the top is always an X, and everything on the bottom is always a dot. And because of the segments, that current direction never changes. It's always with respect to looking at this thing. Even though the rotor's moving, the current's always going in on the top and coming out on the bottom, or vice versa. So if you do the right-hand rule, actually I think I've got this backwards. X going in, dot coming out. Actually, I think it's right because I was looking at it all depends on the orientation of this angle. So there's a 90 degree anyway. It's going to go one direction or the other. I know I spent a lot of time on this picture driving through Nebraska in the back of the car on a family vacation. So I know this picture's right. Anyways. So what happens, though, is every time you add a commutator segment, we're going to call this little value here, this is the CA. And it's kind of like a turn, but it's going to call a conductor, a commutator conductor segment, C sub A. The other thing they do is the armature winding may have more than one layer of, each one of these is one turn, so there's a turn per I think there's a conductor turn per slot, but if you have more than one, you might actually double them up, so you might have 2 or 3, and that's what this M is right here. So the result is that, as that's what we're showing right here, I've got more conductors per slot per segment, and as a result we come up with an equivalent armature winding turns. And this is the thing that you need to remember about DC machines. So we have a turns function for the armature. It's CA, number of commutator segments, divided by M, which is the number of conductors per slot, and then 2 is the number of basically coil ends, which you only have 2. You have an end going in and an end going out. Somebody tell me you can still hear me. You guys with me?
Yeah.
Good, and you can see my screen, I assume.
Yes.
Good. Okay, so what happens in general is, I'm going to skip through some of this, and what I'm going to do is I'm going to summarize these slides to what you need to know. So let's go to the final expression for the induction, for the DC machine, for torque. Okay, so first, to get there, and I'm going to take about 3 more minutes, we have a torque expression which is a function of this angle. This is the armature MMF. Now what this is a field MMF here, the field, but it's in terms of a flux. This is the equivalent to what we called phi P with the synchronous machine, except when it's a DC machine we call it phi sub D. And why that is because it's really what we call a direct axis flux. And I'll re-review this at the beginning of the next time. And this is the flux that is going in this direction here. So you've got your flux flowing from the field. That's phi sub D. And what in a DC machine, and this idea gets carried through into motor drives and all kinds of electronic controlled machines, because if you really want to control a rotating machine, you want to make it look like a DC machine, where you have 2 you have two distinct axes. You've got an axis along the field line, which is the direct flux axis, and you have an axis along the armature line, which controls the torque directly through current. You can indirectly control the torque with the field, but the best, generally you use the armature to control the torque. And this is called the Q axis, quadrature axis. This is called the direct axis or D axis. And so the flux per pole is equal, should have kept my colors right, but this is your D axis here. The flux per pole is equal to the direct axis flux. Now the synchronous machine has a direct axis flux, but it's the flux per pole, depending on the angle of del, only some of the flux, maybe the large portion of it, will end up in the direct axis, but not all of it. And so that's the difference. All of it is ending up in the direct axis with the DC machine. And it really has to do with the angle del and this expression here. So if this is 90 degrees, all flux in the D axis. Therefore, all the armature MMF, which is this, is all in the Q axis. And now you can control the torque and the field independently, even if you have electronic controls on this thing. So we're going to pick up next time. I'm just going to show you this is the actual physical machine. This is from the textbook. And I'm just going to summarize what we'll do, and then we're going to go on into induction motors about halfway through if my machine doesn't reboot. Let's see, where were we here? Trying to get back to that picture here. So we're just going to quickly brush over. This is the turns function of the armature winding here, and it doesn't look like a sine wave. It looks like a triangle. And then we end up with a MMF in the air gap, very similar to what we had with the synchronous machine. And we end up with an expression. We have the turns for the armature and then the MMF for the armature. And that's simply derived from the shape of the MMF, the 8 over pi squared and all that. And then these are just formulas. Sadly, we're going to end up with a formula. The important formula that we are going to use, though, is this formula right here. So we're going to kind of quickly get to that, and we will have a formula for the torque that is directly proportional to the amplitude of the current in the armature, the flux in the direct axis, and this is your winding and your geometry. And so these three things make up your torque, and a DC machine is a very, very simple machine. Okay, any last minute questions? You still there?
Yeah, we're still here.
All right. I think we're done then, and for this time, I'm going to clean up these Module 6 notes as far as what we're going to cover, and then I'll post that. Practice.
Very good question, if you don't mind, sir.
Yeah, sure.
So how you, in a DC machine, what's the mechanism to change the inductance?
Yeah, the inductance, actually, interestingly, we're going to get into this a little bit. It's a DC machine, so the inductance really only affects the dynamics of the machine. It doesn't affect the steady state behavior. But the inductance really, you can think of this. Your question is a good one. I don't like this expression. If I could rewrite the book, but I'm using it because of that. This really is lambda A F times IA, I times the armature current. That's if you take the drives class, the first thing we talk about, teaching that next semester. So there's the inductance LAF right there. So if you were to say what's LAF, that's equal to lambda AF O divided by I field current. Dividing it out. So there's your inductance. Does that answer that question?
So what caused this inductance to change? Because in order to have a torque or a force, we need the fluctuating inductance.
Yes. Okay.
I don't see that. Theta, what is it?
It's a little bit, okay, so what's happening it's a little bit more complex with the DC machine. It's changing because of the movement of the rotor. So if you were, what's changing is the MMF of the rotor. So the thing it's not the inductance associated with, what's really happening is, so here's you remember in the synchronous machine we had the synchronous machine had a L on the field, or the LAF, which was a function of theta R. With the DC machine, the LAA is what's changing, of the armature. And it's associated with this. So this is the turns function of the armature, and because the armature is on the rotor. So the actual mechanism of torque production is happening on the rotor, and so it's a little hard to get your head around it, because it's almost like if you want to see this torque del energy with respect to theta R, you have to put yourself on the rotor and look at it from a rotor perspective. And that's because the current is shifting directions in these little, every time it passes by a commutator segment. So it's really at these points where the brushes make the change in current flip. And I don't know, it's not a great answer, but it's a complicated thing. I'm going to show you an animation at the beginning of class next time that might make this a little clearer. Does that help, kind of?
Yeah. Actually, they speak about it in the book, but they didn't say why we need to make it this way. So I was asking myself, okay, I have two different of signals. One is AC, the other one is DC. But they say with the AC we do it this setup, with the DC we do it the other way. And the only hint they have, they say, because the rotor is a lower energy, and easier to turn the machine when you have a higher energy acting on a lower energy, not the other way around.
Yeah, I don't get that. Well, okay, I guess so. Here's what I'm trying to tell. This is my perspective, and these notes I wrote are my notes. This is my way of looking at it. The field winding has a lot of stored magnetic energy in it. And the field winding is what you're really trying to align your armature winding up with to get torque. And since my field winding is on the stator, my field winding's not, the MMF is not moving. And so that's why I have to have the commutators to make, from the perspective of the field winding, it has to look like the armature is at a fixed angle. That's what the commutator bars do. And so the torque production is a result of this angular difference right here. That del. That's the torque production. If that del were 0, if you were to move the FA up here in line with field, you'd have no torque. You couldn't be able to produce any torque. And it really, it's like I say, the DC machine was kind of a physics experiment that grew a life of its own. It was a physics experiment that was really trying to prove out Lorentz force law with a rotating machine and using battery supplied, or DC is the kind of current that people had at the time, energy, and they would make this big magnet and they would try to produce some kind of force and torque on the shaft, moving it while keeping these guys lined up. That's my idea, is wherever the field is, what the field's doing, the armature displacement from the field is what makes your torque, and it's a fixed angle. And so if the field's moving, the armature has to move. If the field's not moving, the armature has to not move. And that enables you to keep this torque, this angle fixed, and that angle defines the torque. Does that help more, or a little? And we'll show the animations. I think it might help.
Yeah. Okay. Thank you very much.
Yeah, sure. I don't think a textbook does a good job of explaining this, but it's not an easy thing. I tried to. My oldest son wanted to build a motor for his science project when he was in 3rd grade, and he actually understood it pretty well, but it was a real pain trying to get it to work in our basement, and none of his teachers believed or could understand what we were talking about, so he didn't get a good mark for it. We actually got the thing to spin. It's really tricky. You try to build one of these things. It's really weird. So, anyway.
Can I ask a quick random question?
Yeah.
Just because I have a lot of power tools. So are brushless motors basically a DC motor that uses like electronics instead of a commutator?
You're right. It is, but but a brushless DC machine is actually a synchronous machine. And what it does is the brushless DC machine so basically all really efficient motors have permanent magnets in them, okay? So think about a DC machine. It's got these brushes. These brushes wear out and they're clunky, okay, and they take up space, right? And they do a mechanical alignment of these MMFs, and the permanent magnet is where these green spaces are here. And so if they move the green permanent magnets back onto the rotor, and they actually come up with 3-phase armature windings on the stator again, they just control them differently with power electronics, and they mimic the action exactly of a commutator. And that's what a brushless machine does. So it looks a lot more like a synchronous machine, where we had this picture. Where the heck is it? Back here. It's a synchronous machine where they can control they electronically control the angle to 90 degrees through the transistors, and the transistors commutate the direction of flux. They don't so essentially in a brushless machine, the transistors commutate flux direction. In a DC machine, the commutator commutates or changes the direction of current, not flux.
Okay. Thank you.
Yeah, it's pretty interesting, and we talk about brushless machines in the drives class, and it's a very cool thing. It's a lot of fun to design a brushless DC motor control. It can be done with simple logic and Hall effect sensors, and they come up with all kinds of better ways to do it, with these power tools now. There's a lot of technology in that. If you go to work for Milwaukee Tool, they do this stuff there. I mean, that's a pretty good company. They do some pretty cool